A second method for finding the x-intercepts, the zeros, the roots, of a quadratic, if you don't like to factor, is called the quadratic formula. And what it does is it takes a standard form quadratic and it puts it into this little recipe. And the recipe we can show comes from completing the square, but I don't think at this point you need to know that. Let's look at the recipe. The recipe says my x-intercepts, or my solutions for x, are going to come from a formula that says negative b plus or minus the square root of b squared minus 4ac all over 2a. Now what you need to know here, a, b, and c are numbers. Notice there are no x's in my formula. The b comes from this value in front of x, not the x, but the value in front of x. Likewise, the a comes from the value in front of the x squared. And then the c is this value on the end that's located there. So you just have to pick off the values for a, b, and c and basically plug it into this recipe. So a is 1, b is 3, and it looks like c is 0 because there's nothing there. Plugging it into the recipe, it says negative b. Notice I took opposite of the positive 3, plus or minus b squared. 3 squared is 9, minus 4 times 1 times 0, all over 2 times 1. Now simplifying this, I get negative 3 plus or minus 4 times 1 times 0 is gone. The square root of 9 is 3, and it's all over 2. Now, if you recall in a quadratic, we have a choice of getting 2, 1, or 0 solutions depending on where they're located, where the zeros are located. Well, the square root of 9 is 3, and so when I look at that plus and minus, I get negative 3 plus 3 over 2, and negative 3 minus 3 over 2. Negative 3 plus 3 over 2 is 0 over 2, which is 0. This is negative 6 over 2, which is negative 3. So graphically, I have found these values, and they would be at 0, negative 3, and it looks like the a value is positive, so this would open up. Now this was method 2. If I would like, I could actually go back and use method 1, factoring. And if I look at the two quantities that multiply, it'd be the x and the x plus 3. And using my zero product rule, I see the 0 and the negative 3. We often like to use this recipe called the quadratic formula because not every quadratic will factor or come out to have these nice solutions. Let's try another one. Before I can identify a, b, and c, I have to have my quadratic in standard form. In other words, I have to have it equal to 0. Identifying a, in this case a is 1, b is negative 4, and c is 4. So plugging it in, this is my solution for x is going to be negative b. Notice in this case it makes that b positive. So it's negative b plus or minus the square root of b squared, I'm going to put that in there, minus 4 times a times c, all over 2 times 1. Now simplifying this, we always like to look on this inside here. If I multiply 4 times 4, I get 16, and it's negative. When I square negative 4, I also get a positive 16, so I'm going to get x equals, 2 negatives make that a 4, plus or minus 16 minus 16 all over 2. Well, that's just 0. So when I add 0 to 4 and take off 0 from 4, I just get a value of 2. So what would that look like graphically? Well, this is a situation then. If you only have 1 on your axes, and that being at 2, my parabola has a 1, so it's opening up. That's a case when only my vertex sits on my axes. The last one, we know it does not factor. We could show that it does not factor. So I'm really kind of stuck using this formula. However, I think the formula is easier than trying to factor all the time, because the formula will always work if you have a quadratic. So identifying A, B, and C. Notice it's in the right form. So my formula is negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a. So as I say the letter, I just replace it with its value. 5 times 2 is 10 times 4 is 10 times 4 is 40. And I get this negative 4 plus or minus the square root of a negative value. That negative value is 24. So what happens here is that I don't have a square root of a negative number. That does not exist in the real number system. So if I can't find those roots, that must tell me that this somewhat narrow parabola opening up does not hit my axes. Now I really don't know if this narrow parabola is anywhere up here, but I do know it's opening up and not hitting, so I know it's in these first two quadrants. But there is my parabola, and I see, I don't see my solutions. So we say that they are what we call imaginary. Who is telling me about my solutions? This idea called a discriminant. This number inside the square root starts telling me things about my solutions, roots, or zeros. And what it tells me is this. If my number inside of the square root is greater than 0 or positive, it's good to go. I'm going to have two real solutions, and my graph then has two places in which it crosses. If it's equal to 0, if you recall, if I add or subtract 0, I get the same value. So I only have one real solution in its picture is going to be just that vertex on the axes. And the last case, if it's less than 0, if I have a negative in here, and that means I can't see them in the real number system, so there's no real solution. So my graph then looks like this. There are two solutions. They're just not able to see them in the real number system. So we have this new little definition called an imaginary number. An imaginary number is when you take the square root of a negative 1. We're going to define that to be I. Now notice my I is kind of a script I, and that's imaginary solutions. They're imaginary, we don't see them, they are there, but we can't see them in the real number system. So just to kind of look at the square root of 9, negative would be the square root of negative 1 times 9, which would be 3i. The square root of negative 81 is a negative 1 times 81, which is 9i. This would be 10i, and this would be 4i. These do not show up as solutions in the real number system, so we actually have a separate number system called a complex number system. Imaginary numbers fit into that.